Hello, grade 11s. Welcome to this physical science lesson. My name is Gillian, and today we're going to look at the big ideas around another one of Newton's laws. So Sir Isaac Newton gave us the 3 laws of motion, and we need to look now at his law of universal gravitation, which is very interesting. So let's have a look at the screen, and we see that we have already discussed his first law, his third law. Now, why those are together is because we have to usually answer them in words and explanation. And then Newton's second law we've discussed as F net equals ma. Okay, so that pops up again every now and again in this law of universal gravitation. So the one that we're really going to get into today is this law of universal gravitation. There are a couple of areas that we need to look at, big ideas. So we're going to start off with looking at the graphs that come out of his relationships between the force, mass, and distance between the objects. Then we're going to look at the equation that we use. We're going to check out big G and little g, and then hopefully we'll have time to go through some practice questions and to see how we're going to apply our theory knowledge. Right, so let's get right into it. Here's law of universal gravitation. So what I need to say to you is this. It is a universal law, and the reason why it's a universal law is because it's not just telling us about the force of gravity on us and our Earth. It's actually between 2 bodies anywhere. So it could be 2 objects, it could be 2 planets, it could be us and our planets, it could be an astronaut and the moon. So we're talking about any 2 bodies in the universe and how they are related according to a force. So Newton's law of universal gravitation is about 2 bodies and how they interact. So we're going to look at these 2 bodies. You can see here on my screen, I have a really big one and I have a little one. Now those 2 bodies will have mass. So all bodies have mass. All objects have mass. All entities have mass. If they didn't, they wouldn't exist because they're all made up of matter, right? So each one of them is going to have a mass. They are going to be attracted to one another by a force. And what comes into play here is how big the masses are or how small the masses are. The other thing that comes into play is distance. So this distance between them. So obviously it makes sense if 2 bodies are very close together, the force is going to be quite big, and if they're far apart, the force is going to be less. And the same with the masses. If you've got objects that have got less mass, the force is going to be of less in nature, and if the masses are big, then the force is going to be a big force. So let's have a look and see exactly what Sir Isaac Newton worked out about the relationship between these 3 things. So when we're dealing with variables that are so different and so many, we have to choose one variable to remain constant. So that's what Sir Isaac Newton did. Have a look here. He kept distance constant. That means that we're not changing it. The variable is constant. The thing that will change then is the mass and the force. So we kind of move distance out of our relationship for now. The masses are then changed, and the experimenter, the scientist, Sir Isaac Newton would have done that. So they changed the masses. So those are variables that are independent. In other words, they are changed in a way that we know. So on the x-axis, we always write the independent variable. And so the dependent variable is going to be the force. So the force is dependent on the masses of the objects. And what Sir Isaac Newton found was that the force was proportional, that little fish sign, to the product. We're multiplying it together, the product of the two masses. So mass 1 and mass 2, when we times them together, we get a force that is proportional to that. Now, that sign we would say is directly proportional. That means that as the one increases, so the other is going to increase by the same amount, by the same factor. The way we can tell and prove that this is a directly proportional relationship is if the straight line passes through the origin. So that's the origin there of our graph, and the values for that point is going to be 0, 0. That means if we've got 0 mass, then we're going to have 0 force, which makes sense, right? There's no mass. In other words, there's no objects for a force to work on. So at the origin, the line has to go through that origin to prove that we have a relationship which is directly proportional. So just as the product of the masses increases, the force will increase. If the product of the masses decreases, that force is going to decrease. And that decrease or increase will happen by the same factor. So that is the relationship that Newton found between the product of the masses and the force. Now, because there are 3 variables involved here, we have to go a little further. And so the second round of experiments would have kept the mass constant. So now we're dealing with objects that have constant mass. So what is going to change then? Well, the distance between them is then changed. Again, this is something that the scientist would do. And so R is the independent variable. The force is going to be dependent on that distance. So it would make sense that as the objects have moved further away, the force is going to get less. As the objects are moved closer together, the force is going to get more. But what Sir Isaac Newton found out was that it was an exponential relationship. In other words, excuse me, as the objects got closer together, the force got way bigger than was expected. And he discovered that it was this exponential relationship of actually distance squared. Now, you would say maybe that this graph is representing something which is indirectly proportional. However, we have to prove that. So the way that we prove it is by manipulating the data and by changing it around. You can see here, I have turned the data around, and for that straight line to then pass through the origin. Only once this straight line graph passes through the origin can we say that the relationship is inversely proportional. There are 2 ways of writing it. So we can write it like this: the force is inversely proportional to r squared, or we could say that the force is directly proportional to 1 over r squared. So we are still sitting with a relationship. And this relationship has to be changed into an equation for us to use. And to do that, we have constants. So we're going to get to the constant in a moment. But what is important here is the definition of Newton's law of universal, remember, because it's about any body in the universe, universal gravitation. So this is a definition that you have to learn off by heart. It is Easy marks. You need to have everything included in the word. So let's have a look at it. So each particle in the universe, there we go, the universal gravitation, attracts. So we're talking about an attraction. Every other particle with a gravitational force that is directly proportional to the product of their masses and inversely proportional to the, wait for it, square of the distance between their centers. Very important that you get all those words in. So here we have this, this constant, and there it is there, G, it's a big G. You will find that value on the data sheet. It is 6,67 times 10 to the minus 11. It's very, very small. But this is going to give us a force that is magnitude only. In other words, size. How big is the force? And that is because we are seeing this force as a force of attraction between two bodies. So the direction is seen as the attraction between the bodies, so we don't need to put a direction because we know that it is two bodies attracting one another. If it is negative, if your answer is negative to these questions, then something is wrong. So the force will never, ever be negative. If you get a negative answer, you need to go back and you need to check that you have done, you're going to recheck it, that your answer is correct. So here's our equation. This is the equation we're going to use. Now there are two values, a G, big G, and a little g. So big G we've spoken about, that is the constant, and that we get from the data sheet. Now, little g is the effect of this force. It is not a force itself. I made a mistake in the last lesson and I said that it was gravitational force, so we all need to be careful. It is actually acceleration due to gravity. So acceleration due to gravity, due to the gravitational force, and that is going to change depending on what planet you're on. So on Earth, we know that our G is 9.8 meters per second squared. If you're on the moon, it's going to be a lot less. On Mars, it's going to be a different value. So acceleration due to the gravitational force of a planet is going to be specific for the planet that you happen to be on. Okay, so we know this from Newton's second law. So F net is equal to ma. So the acceleration due to gravity is, now what we do is we change this to a little g, so you can see there, and instead of acceleration we put a g, which is the gravitational the acceleration due to gravity. So in place of m is going to be the mass of our object, and then in place of g we would write whatever that value is. So now on Earth it is 9.8 meters per second squared. Right, grade 11s, it's time for a break. When we come back, we're going to see how we can use this information in solving problems. Welcome back, grade 11s, from the break. Let's dive right in. So, how are we going to be asked these kind of questions? There are three ways that we would be asked to solve these questions. So let's look at my board. So substitution, so straightforward substitution into an equation, given information, and we pop out an answer. Okay, simultaneous equations, and then reasoning with ratios. Now, reasoning is quite tricky. So we need to look carefully at those, and we're going to get to one of these in a moment, where we've got to figure out how the one planet, let's say, is related to the other planet. Okay, let's move on. Let's get right into it. So I have this question. The gravitational force on a probe called Curiosity, so that's its name, probe's name is Curiosity, on the surface of Mars, okay, not on Earth, on Mars, is, and it gives us the amount of the force. The radius of Mars is so much, so 3,390 kilometers, and the mass of the planet is 6,39 times 10 to the 23 kilograms. Calculate the mass of the probe. Okay, I've drawn Curiosity here. It's a very weird drawing. If you're going to have a look at some photographs of Curiosity, you'll see it's got all sorts of things sticking out of it. All of these experimental arms that pick up samples. A very interesting little buggy that moves on the surface of Mars. Okay, so we want to find out the mass of that. So we have Newton's law of universal gravitation, and we get that equation from it. The force, we know, they've given that to us, force we know. G, big G, we're going to get from our, it's the constant, we're going to get it from our data sheet. Mass 1, they've given us a 6,39 times 10 to the 23. Mass 2 is what we've got to find. So that's of our buggy, that's of Curiosity. And then the radius they've given to us as well. However, they've given us the radius in kilometers. So have a look here, in kilometers. So we need to be awake and wary of that. So we are going to change that into meters, because that's the SI unit that we're using for distance or radius. So times 10 to the 3 meters. So we've changed that. Good. So all we need to do now is substitute in our values. So we've got 3,338 newtons for the force that this buggy experiences, the probe experiences. Our gravitational constant is 6,67 times 10 to the minus 11. And the mass of Mars is 6,39 times 10 to the 23. We have got mass 2. So that's the mass of the probe that we're trying to find out. Is there any trick around the radius? No, don't think so, because Curiosity is sitting on the surface of Mars. So it's not above, it's on the surface, and so we can take this value for r as the radius as the distance between the object, which is the probe, and the center of Mars. So we're going to write that down, and we've already converted it into meters times 10 to the 3 meters. What do we have to do? We have to square it. So that's something that is a common problem, is that we forget to square the distance or the radius, and we get into trouble. So be aware of that. Right, now you're going to use your calculator. I have calculated this, but for time purposes, I can't show you. So once you've calculated these things, well, the way that I've done it is I have times these two together, and so I get an answer of 4,262 times 10 to the 13 times my mass 2 divided by 1,15 times 10 to the 13. So now I would have to rearrange my values to get the subject of the formula to be M2. And so I'm going to do that. I would write M2, and it is going to be 3,338 divided by all this calculation here, all that calculation, and that is 3,7087. My answer here is 900 kilograms. Now, I know on your calculators you can store your answers, and you've got your special ways of doing that. So make sure that you can use your scientific calculator with all the times 10 to the 23 and times 10 to the minus 11 and the squaring, and that you can come up with an answer which is good. Go back and check your answer. Right, so there we go. That is the mass of curiosity. And let's move on to the next question. Okay, so calculate the acceleration due to gravity of the Earth 2,6 times 10 to the 3 kilometers above the Earth's surface. So here's my yellow dot. We can see that it is above the Earth's surface, and that is 2,6 times 10 to the 3 kilometers. The mass of Earth I have given you, that you will find on your data sheet. The radius of the Earth is also from the data sheet. But have a look here. We have got mass, and we have, meters, and we've got kilometers. So that needs to ring a bell in your mind, and we need to convert that to meters. So kilometers to meters. Sorry, let's just erase that so that I can write it a bit better. Here we go. So times 10 to the 6 meters. Excellent. So here we have Newton's equation of universal gravitation. I have replaced the F with mg. Okay, and we have the mass times the mass of Earth divided by the square of the radius of Earth. Now, there is no mass for this point. It's just saying what will the gravitational pull be on the Earth, from the Earth at that particular point. So we really don't need to put this mass in. Okay, it isn't, we don't need it. It's not what we need to use. So we end up with this formula here. G is equal to the constant times the mass of Earth divided by the square root of the radius. So G is 6,67 times 10 to the minus 11. The mass of Earth is 5,98 times 10 to the 24. Now, we've got to be careful because the radius of Earth is this amount here, but there's an extra bit over there above the Earth's surface. So our radius is only from the surface of the Earth to the center of the Earth. We need to add the extra bit that's above the surface of the Earth. So we're going to add that in, and we get the radius, which is 6,38 times 10 to the 6, plus, let's go back and see that value that we calculated. So 2,6 times 10 to the 6, 2,6 times 10 to the 6, and then what must we do? We need to square it. Square that whole value. So we add those two together and then we square it. Once we've put that into our calculator, we get an answer of our gravitational acceleration is 5,1 meters per second squared. And which way is it going? Because this object, or if we were here, if we were here, okay, we wouldn't be floating off in that direction. We would be pulled towards the center of the Earth. So this would be 5,1 meters per second squared downwards. Right, grade 11s, we've come to the end of our lesson. I hope to see you in the next lesson where we are going to be looking at a few more of these problems. So come and join me then.